this talk is about the scientific machine learning. Instead of from statistic point of view, I'm looking at machine learning from numerical analysis point of view. So that's the reason we asking the very different questions and more like numerical PDEs. So this is the title of my talk. As you see that I call that a least square neural network method. Instead, I call that a physics informed neural network, PIN, for this problems. Basically, I'm looking at from numerical PDE point of view to examine, to ask the questions, how can we design a numerical scheme which is competitive, which can compete with the existing mesh-based method. The problem I'm choosing is a scalar hyperbolic conservation law. Basically, we think about neural net have some benefit to do that. This is my collaborators. Okay. So this is the outline of my talk. I will first introduce what's the still challenges for hyperbolic conservation law. And then I introduce why we should use a neural network. Then in order to apply the use a neural network, then we have to use this square type of approach. So in this is my website. I have several papers about the neural network approximations. Okay. So when we're looking at a scalar nonlinear hyperbolic conservation law, if you're looking at here, it's very simple equations. Unfortunately, if you compare with this is a problem we still consider computationally challenging because of these two main difficulties. One, of course, this problem has the issue about uniqueness, right? Then you have to introduce the entropy condition, etc., to deal with that. So here I'm not talking about this part. The main part about the computation, the solution is discontinuous. That's what I would usually talk about a short. Discontinuity is not bad in terms of approximation theory, but when the interface or the location is unknown, then it's much more difficult. So let me use a very simple example to show that. So suppose we have a step function in 1 dimension. If we knew the interface C, then I can approximate this is a step function by this is a piecewise linear functions very well. And particularly, you can easily compute this error estimate, which is in the infinitive norm. Of course, you don't have the approximation. This is half. If you're using LP norm, then it depends on the gap between depends on the size of the epsilon. If it's p equal to 1, then you get a linear order. If the p is large, p, for example, L2 norm, then you get the only square root of epsilon, right? So if we knew the interface, this is a simple problem. We can approximate very well by continuous piecewise polynomials, linear functions. Then the question is, when we apply to the hyperbolic conservation law, when we don't know the interface, what can we do, right? So it's natural to ask the question, if I don't know the C, I'm using the existing function class to approximate this function P, what can I do? Now, as you know that all the numerical scheme, the finite difference, finite volume are based on based on the fixed quasi-uniform mesh. If I'm doing that, so I can approximate P or compute P exactly instead, then I have to use very, very fine mesh. So my mesh size has to be very small, epsilon. We're doing this sense because we don't know the C, automatically we have this numeric artifact. So we have overshooting, oscillation, all these kind of problems. And then we have a lot of post processes how to get rid of this numeric artifact. Then, so natural question is, do we have a better function class to approximate these functions? So basically the mesh-based method has been well developed for the past 50 years. It's a universal approach. It works very well for a lot of problems. And if you think about the philosophy of this is approach, basically, when we start approximation, we even don't ask in what kind of function we're approximate. And we partition the domain first on a fixed mesh. Then when mesh size is going to very small, then we in generally will produce a good approximations. So naturally we're asking that, is there any other class of function we can approximate that? Right? Well, for one dimension, even in the 60s, there is one we call the free knot spline, and there are many research on that, basically up to the late of the 80s. And find the free knot spline actually provide very good approximations. Let me show you that. If I'm using the free knot spline, actually I only need two basis functions. Or if I use a neural network notation, is I only need two neurons. I will explain what this neuron is. Then I can approximate this is a P. I can represent this a P exactly. And the approximation, you can do the same error estimate. Only thing here is the epsilon is any number you can, epsilon is not the mesh size. So the order here is not important. Epsilon can be as small as you expect. Okay. So now, of course, the reason of why we didn't use the free knot spline for the numerical PDE, one of the reasons for that is, as a mathematician, we're not able to extend the free knot spline to multi dimensions. That's one issue. The other issue, of course, and how to choose the mesh point or free knot. That's a very challenging problems for optimization, right? So recently, because the popularity of machine learning, one of the magic machine learning is the neural net. So let me all this is three speakers talking about this neural net. So everybody familiar with this is a network structure. And here I'm using the formula to represent that. So let me give you a little bit more explanation or some kind of understand. Well, we still don't understand the neural network very well. So here, only looking at from one point of view, I treat the neural network as a new class of approximating functions. So I'm very looking at this sense in a very narrative view and completed from the approximation theory, right? So this one looks very, very complicated. We have so many hidden layers, and I believe right now we don't have much of understanding what's the rule, what's the of layer, and what's the rule of the neurons. So I just give you what I understand. So one way you can think about that is start with this independent variable x. Then we produce a function I call the u. And if you are writing in this way, as you can see that u essentially is a linear combination of 1 and the neurons in the loss hidden layer. Okay. So in a way you can think about this 1 and the loss hidden layer provide a basis function. And the output of this network give us the linear space if you only looking at the loss hidden layer. Now, of course, it's not a linear space. Then the question is, what happens with the neurons in the previous layers? So in some way, you can think about all this is a neuron in the previous layers is sort of like prepare the best basis function in the loss hidden layer. Okay, so let's looking at the one hidden layer ReLU neural network. So they have a simple representation like that. And if we fix the weight and the BIOS, then you can look at all the function in this set is a linear combination of 1 and this neurons. So that's the reason I can explain this one is the generated by this kind of basis function. So here I give you one more understanding of that is if you fix this as a weight and the bias, then you can show that 1 and this is neurons are linearly independent. So the geometrical meaning of this neurons essentially they produce some hyperplane. On the one side is equal to 0, on the other side is linear. Okay, so this is a geometric. The pictures of this is a breaking hyperplane, and this is one of sense if I'm using the one hidden layer neural network to approximate. This is a Scalar function we usually use as a benchmark test problem for mesh refinement. So this is the break line generated by that functions. What you can see that is instead of we're using the fixed mesh, this neural network actually generate a continuous piecewise linear functions. But the partition is very different from the mesh-based method. It's very, very irregular. Okay, so the question is for hyperbolic conservation law, we want to approximate a function which is discontinuous, and also we don't know the interface. To do that, we recently proved a theorem. But basically, the reason we're doing this one is we want to understand what kind of architecture of a neural network can produce a good approximation to step functions or to the discontinuities or to the shocks. So what we show is the following. If with 2 and 3 dimensions, we only need 2 hidden layers. Now, if we are looking at the continuum mechanic problems, then that's enough. So essentially, if I only interested in approximate shock, I only need 2 hidden layers. For some problems, if it's a space dimension is from 4 to the 8, then we need 3 dimensions. And we can show in some strong norm because we're looking at hyperbolic conservation law. And the error to approximate this is a step function is square root of epsilon, and epsilon can be any given accuracy, any numbers. And alpha 1 and alpha 2 is the jump. Okay. So let's apply this neural network to solving the hyperbolic conservation law. The first problem I'm looking at is a linear advection reaction problems. I'm writing in this way. So this is advection term. I'm writing in this way. This means the directional derivative of u along the direction beta. Instead, I'm writing in the partial derivative along the coordinate because once I write, because the reason I'm doing that is because the data g could be discontinuous. When g is discontinuous, when we write a partial derivative along the coordinate way, then physics does not make sense. So that's the reason, or the derivative does not exist. So that's the reason I'm writing that along the direction, along the velocity directions. Okay. The first sense is if you want to use the neural net to solve in PDE, because neural net is a set instead of a linear space, so we cannot use an equation. So that's the reason we have to rewrite this as a equation in some minimization form. Because this problem is non-symmetric, so there's no natural minimization principle for these problems. So that's the reason when we have underlying problem does not have a minimization principle, then we create artificial one. Now, of course, naturally we're using the d-square, right? For this problem, basically we can apply L2 d-square. You can apply the other norms. I'm still not convinced the L1 norm or other LP norm will help. So L2 norm is the easiest one. So I'm going to do the L2 norm of that. In particularly, about 2004, there is a mathematical theory. If you do this L2 least square for this problems, they can show that the homogeneous functional is cursive and also is bounded. So that basically guarantee this square problem is well posed, right? A little bit is when you go in this approach, you do require some additional conditions which we don't need. Okay, so once we have this least square formulation, then we can use the neural net instead of finite element space, right? So I can minimize this is a least square functional in the set of a neural network. So that's basically what we do. Now, that's the reason I call this a least square neural network method for the linear problems. Well, when you use a neural net, the numerical issue is very different from finite element, because a finite element is based on a fixed mesh. A lot of things is known. Then, for example, when you evaluate this square functional, we have to do the integration. The numerical integration, it is very important. So if I'm using statistic approach, then probably you are using the random distribution of the integration point. But in generally, that's not a very good approach for that applications, because we don't know what the integrand is. How to choose the integration point is very important. So basically what we do is we are using adaptive numerical integration to do that. Well, in generally, if you don't know how to do that, if you can afford, you can use a very fine integration mesh, which has nothing to do with the neural net. Okay, that just basically provide you the right information to do this minimization. The second part of that is the numerical differentiation. If you're looking at a finite element, when we use the weak formulations, all the derivative makes sense, right? But here we're looking at the strong form. So the differentiation, if you do the automatic differentiation as a pin, or doing the finite difference along the coordinate, in generally, you are not followed physics. You are violate physics. So instead, that's the reason I'm writing this as a derivative in terms of the directional derivative. When you do the numerical differentiation, in this case, for this linear case, you should follow the direction. So instead, we're using the discrete directional derivative. This actually is very, very critical. If you're looking at when we wrote this paper, actually, all the pin completed fails is simply they didn't do the differentiation right. As imagine that if your solution is discontinuous on the interface, there's no meaning about the derivative. Only the derivative makes sense is along the beta direction. Okay. Finally, once we discretize that, we end up with an algebraic system. In this case, it's a nonlinear algebraic system because the weight and the bias inside of neurons. Then, of course, right now it's very difficult. This is one of the things keep people away from the neural net-based approach, because to solving the nonlinear algebraic system is very difficult. And currently, we have the method of the gradient descent and other things. This part is still a bottleneck for the mesh-based method. Okay. So once we do in that sense right, then you can, of course, as a numeric analyst, you can do the estimate the error. Even this one is not linear space, you still have that quasi-optimal approximation like a C's lemma, right? The second part is because the solution is discontinuous, the way we can get a priori estimate by decompose the true solution to the two parts. One part is a smooth part, one part is a discontinuous part. So for the discontinuous part, neural net can approximate extremely well with the accuracy of the square root of epsilon, and epsilon can be any positive number. So essentially, we don't have any issue about the approximation of the discontinuity. Instead, we have a standard approximation for the smooth part. Okay, so that's basically a very simple theory for that. Let me show you what's the numerics. Now, everybody see that even it's a simple, this is a very famous model problem for the hyperbolic conservation law, ut plus ux equal to 0. If you do the, if you put the initial inflow boundary conditions, or initial is the 0 on the left, on the vertical, and on the horizontal line is a 0, then this produces step functions. The discontinuity interface is this is a diagonal. If you simply just apply the finite element using the mesh refinement, that's one of my friends produced this one. As you can see that they refine the interface using a lot of mesh point. Then if you don't careful enough, then you have the overshooting. Hopefully you see that. So if we do the neural net, as what are we writing that? We only need 6 neurons. We can approximate this function extremely well. As you can see, this is the cross interface, no overshooting, and approximate very well. Theoretically, for this simple problems, we only need 2 neurons, like 1 dimension, because the interface is a line, it's a straight line. Because of the training optimization problems, we need 6 neurons and to do that. Then the next one, of course, if your velocity field is not a straight line, it's not a constant, it's a piecewise constant, then what happens? So if it's a piecewise constant like this one, then if I'm using 1 hidden layer, no matter how many neurons do I use, the solution I produce, they smear out of the shock. That's very typical feature of the D-square. As you can see that from cross section, and the solution is really bad. But instead, if you're using the 2 hidden layers, only using the 5 neurons for each hidden layer, you can produce excellent approximations. Again, no overshooting and no smearing, right? No oscillation for that. And then you can do a lot of, this is the sense. Then the question, of course, when you apply to the neural net based approach, what is architecture? Currently, if you look at it, most of the applications in the machine learning or scientific machine learning, they using the huge, using many layers, and each layer using a lot of neurons. That's one of the reasons people doing that is because we still don't understand the in terms of approximations, what are the right architectures. For that, we wrote a couple of papers about the how to adaptively construct the smallest architecture to approximate the functions or solving the problems. So for this problem, if we use an adaptive neural network method, we can produce that is the 7 and 4. The first, we have a strategy to doing that. This is automatic approach. We produce a very small network, can produce a very good approximations. Then you can make this is much harder. There are a lot of examples for that, and basically show that for this one, I want to show that when the interface is a curve, and even you use the 3,000 neurons, 1 hidden layer, it doesn't doing very well. As you can see, the oscillation error. And if you're using the 2 hidden layers with a 60-60, doing the approximate function much better. Okay, so let me, then for the nonlinear scalar hyperbolic conservation, what do we do? Okay, I'm writing in this way, but I shouldn't write in that way, because we know that for nonlinear hyperbolic conservation law, even we started with the continuous initial, then the solution were, the shock were formed. So the solution will be discontinuous. And we're talking more about that. Now, there are several ways to do the square. In particularly, the people in the Corolla's group, they did other sense. Let me don't mention that. One of the reasons we didn't do that is the optimization is one of the bottleneck. So we're trying to do the simplest least square as we can, Then based on this simple least square, we're trying to make that work. Okay, I will show you how. So I simply applied the least square, L2 norm least square to the original problems. So as you can see, this is hyperbolic conservation law, right, equal to 0. This is the inflow boundary condition. This is the initial boundary condition. Often it's L2. Okay. Then instead, I'm going to minimize this one in the finite element space, no matter it's a continuous one or discontinuous one. Now I'm going to minimize this problem in the set of a neural network. And as you can see here, I do, because the theorem we proved, this is the number of layers. We don't know the number of neurons. Okay, we don't have that. Again, in order to make this one work, we have to talk about 3 things, right? One is the numerical integration. That's basically how to choose the integration point to give you the right information. In the example, what we did is we basically right now, we don't have, adaptive numerical integration is slightly complicated. So we just do the very fine integration mesh. In that way, we don't miss any important information from the problems. The most important part is what is the meaning of this differentiation. The numerical PD or PDE people, usually we're kind of lazy, right? We want to write because the differential equations, because this one looks so simple. But actually, for the experts, we really don't mean that. This one, we do not mean this is a partial derivative with respect to t. This we do not mean is a divergence with respect to space variable. Actually, the whole sense we mean something different, because in particularly when my solution is not smooth, right? As you can see that if my v is discontinuous, then the partial derivative with respect to t does not have a meaning. So that's the reason we have to talking about some discrete differential operators. In this case, we call it discrete divergent operator. So instead, I'm looking at this equation. I'm going to rewrite this equation more back to the physics. This one I can write as the divergence with the space and the time of the total flux. So the total flux, I mean, is the with respect time component is u. Then the other one is usually people call the spatial flux or the flux, right? Then I can write this one. The hyperbolic conservation law, essentially a very simple equation, is a divergence of this capital U vector field is equal to 0. Okay. So now the question is what is the meaning of divergence? So then again, we have to go back to the physics. So instead, I'm going to understand the divergence as a way I can understand that if I'm looking at it's kind of like take any kind of volume, integrate this one over this volume, then I can write as the flux. Then I take the limit when volume approaches to 0, then this is the meaning of the divergence. So when I do approximation, then I basically write it as the following: the divergence of this one, should be capital U. Should be the integral of this surface integral. So now I can use this one, average of this one to approximate the divergence. Okay. So then you can do all this is a standard sense to derive the discrete divergence operators for that. Then you can talking about when your solution is discontinuous, what kind of order approximation you have. So that's the more like for every interface we are looking at, we're consider if it's discontinuous or continuous. Okay, then we can have all this kind of estimations. Let me just go. Don't bother you by this is a. So let me show you what is the numerical examples. So for a simple problem like the inviscid Berger equations. So this is a one-dimensional inviscid Berger equations. F of u equal to the half u square. This is very simple equations. The problem what we have is the Riemann problems. So our initial is 1 and 0, if I remember right. Then if we do this is what we call the least square neural network method for this one, then this is the simulation for the t equal to 0, t equal to 0.2, 0.4, and etc. The architecture what we're using is 1010. Okay, as you can see that if you look at the cross section, it's perfect basically. Everything is there's no smear, there's no oscillation, there's no overshooting, and the number of the parameters is very, very small. Okay, actually we can for this simple problems we can reduce the size of the network more, but we didn't do that. Okay, so this is a rarefaction wave. Rarefaction wave. This is a very interesting in this field. Actually, I'm reasonably new for this field. My original background is more about the elliptic and hyperbolic PDE. I never do anything about hyperbolic PDEs. Okay, so when the rarefaction wave actually, from mathematical point of view, this problem is part of this is a problem. They don't have the PDE model does not have a description about physics over there. Then somehow we're trying to fill up this gap by using the viscosity vanishing solutions. So it's sort of like our physical model does not describe that part of the region, but somehow we want to use a mathematical way to fill up this one. It's very interesting. But anyway, if I'm doing the neural net, if I require my solution is continuous, then automatically what we're doing that we're fill up this gap. So there's no uniqueness concern. And the solution, as what you see, is like this one. Very good approximations. Okay, then we try the different, more complicated. This is a flux with a sign. And then this sense is more like gradually developed to that shock. And that's what you see that in that case, we have to use the trendy. Okay. So now we're looking at the, still is a convex flux, but it's instead of a quadratic, we're using u to the fourth power. So this is the reason we are introduced that the discrete divergent operator. In the beginning, we wrote a paper because we don't understand the hyperbolic conservation law very well. So we're using the Eno and the Wino scheme, using their ideal to construct the discrete divergence operator to approximate the divergence. And what we find that is we cannot approximate this problem very well. This is the, I didn't show you that. So instead, I cannot enlarge that. What you see that is the, if I use the discrete divergence operator, I have to use some kind of a good approximation along the boundaries. Once you're doing that, then you can get a perfect approximation. So this is the, I guess I can say a few more words about that is the, when you're using the Wino or Eno, all this kind of a mesh-based method, they are based on the time marching. So when they do the discretizations, they never consider you have the discontinuities along the time direction. And when you do not put this one as into consideration, then you increase some errors. So that error come back. So this is the a harder problem we did is the for the non-convex flux. One, of course, is a cubic, and the other one, of course, is the I forgot what the name was. So for this problems is we have a compound shock wave. So part of them is the shock, and a part of it is the rarefaction wave. So this one is much more difficult, and for us, because we're using time-space approach, right now we take us a long time. As you can see that we have using the really big size of the network, 64, and 3 hidden layers, and each hidden layer we're using 64. Then take us approximate very long time to training. But still, we get some good approximation. But the I hide in a sense about how long it take us to do the training part. So, but anyway, so we can deal with that. Before I, this is the second, okay. The last example is the Berger equation in the 2D. So this is one of the test problems they use in the piecewise constant sense. We can do that reasonably well. And still we're using the, we should be able to do the 2 hidden layers, but because of the training, we are having to use the 3 hidden layers. Before I, okay, so let me give you the summary. Before I give you the summary, then I just want to mention that for all this is one-dimensional problems, now we're developing the new approach, and a new approach hopefully will written up soon. And even in terms of the computational cost, we can compute this one extremely fast, probably faster than anything, any numerical approach I know. But okay, so let me summarize of that. So first, I want to emphasize the scientific machine learning. Instead, we're looking at it from statistical point of view. We're looking at from numerical analysis point of view. So if you're looking at here, then what we really deal with that is, I believe the neural network is very, very important. Is basically, to me, is the one of the magic for this machine learning. Why they achieve so many make so many contributions in the many important application areas. Now, of course, other magic is the big machine now we have, right? So for the neural network, to me, I'm looking at neural network from very narrow point of view. I treat this one as a new class of approximating functions. Okay. So if I use in ReLU, this class of approximating functions in one dimension is nothing but free knot spline, which was invented by the mathematicians in the late of the 60s. There are many papers about the free knot spline. They understand very well the free knot spline is much better than the finite element. Well, not finite element. In 1D is much better than the free knot spline, which is a fixed meshed. Okay, so we really deal with something. We have a new class of approximating function. We still don't understand it well, but they have a wonderful properties. They basically can move in the mesh, right? The mesh is not artificially man-made. It's more dictated by the original functions. So we can think about this as the moving mesh versus the quasi-uniform mesh. That's what we do for the finite element, finite difference, finite volume sense. And also, in some way, similar to adaptive mesh refinement, but we don't have topological mesh that makes sense much more convenient in a way. The second part is the, when I started this is a machine learning business, or when I look at neural network, then because my background is the finite element, etc., the first question I'm asking that, why should we use this as a new class of function? Or in other ways, what kind of problems we need neural net? So basically, the rule of thumb for myself is anywhere, any problem I need adaptive mesh refinement, then neural net probably have a chance. Then in particular for me is I think about for the hyperbolic conservation law, because we don't know the interface and the solution is discontinuous. I believe this one probably is a very good class for these problems. And finally, from approximation point of view, neural net provide a lot. But in order to train or iteratively solving that nonlinear algebraic problems, this is very difficult. We're encounter a non-convex optimizations. And as you know that for anyone deal with a nonlinear PDE, then automatically we're thinking about the method of continuation. So basically we're trying to provide some good initial, then we can use a Newton or Newton-like approach to do that. So this is still a very, very open field. hopefully in a couple months, I can present you some fast iterative solvers for this is neural net approximations. Thank you for giving me a chance, and thank you for pay attention on that.
Thank you very much, Professor Kai. This was one of the rare, very rigorous mathematical work behind neural networks. Yeah. So let's take some questions now. Yeah. So there is a question from Professor Mario Olberger. How do you adaptively choose the quadrature points?
Okay. You need a posterior error estimation. If doing the least square, how do I explain? Okay, in our paper for the adaptive neural network, let me explain that first. So basically, we start with a one hidden layer with a very few neurons. Then we'll do the standard sense like adaptive mesh refinement. Of course, we don't need to do that. The main thing is because of the optimization. If you don't have a good initial, then it's very difficult to train or to iterative solving that. So instead, we're doing very, very similar to the local mesh refinement. Then basically, we find the physical partition of the neural net. Then we do the local mesh refinement using some kind of a posterior error estimation. At that time, we either decide, should we enhance, we make the network larger, or it's because our numerical integration is not good enough. So basically, what we do is we're trying to refine mesh based on that procedure. And if we find more times, if it does not improve the error, then we switch to increase the number of neurons. So hopefully that answer your question.
I guess yes, it answers the question. Thanks. Thank you very much. I also have a question that when you say adaptive, how do you decide whether to be adaptive in number of neurons or the number of layers?
Okay, that's a very, very good question. That's very difficult. The main reason it's difficult is because we don't understand the neural net well, right? So in the way, if you're looking at everybody, when we're looking at the neural network, the picture we see is this one, right? That's the picture we usually see. So every time when I learn a little bit more about this neural network in terms of the not a series approximation, but the approximations, okay, then I get excited. This is invented in the 1958 by Rosenblatt. He's a psychologist. If you look at that, the structure of that is so pretty. Inside of each neuron is nothing but this is a linear transformations, and then you activate, right? Then the part is we need to understand what is the rule of the layers. What does layer provide you, right? So for us, let me give you a little bit more stories. That is why the mathematicians cannot extend the free knot spline from 1D to 2D. One of the simple reasons is because we are trained to looking at local basis functions. And if you're doing that, then we stop. There's no way we can go to the multi-dimension. But the Rosenblatt never looking at. If you switch to the global basis functions, then automatically you can easily go to any dimension. Okay, so that's simple reason for that. Then the question is what is the rule of the second hidden layer or the next hidden layers? So this one in one way, okay, everything I give you just the only my view of sense. They do give you the local information. Okay, so do I have some picture? Hopefully I have some picture to show you that. I didn't emphasize. Okay, here, right? So if you're looking at this one, if I use one hidden layer, this is the partition I do. It's very, very messy. There's no topological architectures of that. and the shape of the partition is very, very irregular. My solution is terrible, smear out of everything. But if you look at the second hidden layer, this is I didn't have time. I didn't explain. The blue line is the break line of the first hidden layer. The red one is the break line generated by second hidden layer. As you can see that this is a two red line just perfectly located interface. And I can compare the example in the 1D, one simple problem I show you that. So exactly, I locate this interface, and between I'm using the two interface to linear ramp to approximate that. So, okay, back to your questions. I don't know, right? So when I don't know what I do, I basically, the approach, what we have, we introduce a quantity we call improvement rate, which means if I'm adding the number of neurons in the same hidden layer does not improve as much as I want, then I'm starting second hidden layer or the third hidden layer. Sorry, I take a long time to answer your question.
No, it's very clear. It's quite clear. Yeah. Or let's say it can be as clear as much possible, because we also don't know how the neural networks works. But yeah, the second issue is that the second issue was about, you mentioned the initial point. So do you think that transfer learning can be used, for example, to train a model on some simple model first and then start doing adaptively the adaptation for more complicated model?
Yes. I guess okay. Here's the other sense about machine learning. We have a lot with from several different fields, right? Statistics, computer science, and psychology. The terminology you're using is very different. In terms of numerical analysis, what are you saying that it's nothing but method of continuation?
Okay.
There's a subfield in the numerical analysis we call the method of continuation. There's a book about that. There are several books about that. And it's basically the main purpose is trying to provide a good initialization, right? Nothing more than that. Yeah, transfer learning, I believe that's basically ideal. I don't fully understand that, but that's my understanding.
Okay. Yeah, sure. Thank you for clarifying. Yeah. And there is one more question. Would it be possible to use negative norms instead of L2 to deal with derivatives?
Okay. There is a small community. I was there for. We still meet like every 2 years. We have workshop called a least square finite element or this type of sense. So one sense, I more classify the PIN as a statistical approach. Basically, what they do is they do the discrete L2 least square. Once you're doing that, then even they call it a physically informed, but you miss a lot of physical informations. So once you have a PDE, that's a very, very good question. As the question is, what is the right least square formulation for that PDE? Now, of course, -1 norm least square is very popular and actually make a lot of sense. But as you know, that the -1 norm really means you have to evaluate invert some differential operators, like Poisson operators, and it's reasonably expensive. And in a way, I more prefer the L2 least square. That's my view, but it's perfect fine if you can doing that well.
I hope that answers the question. Yeah. Thank you very much. Thank you very much for your talk and for giving for your time. And I would also like to thank all the participants and all the speakers, especially the speakers, Professor Rotsa, Professor Olberger, Dr. Fazel, and Professor Kai for their talk and time. And maybe Professor Wells would like to add something, and we then meet the next week again for some other interesting talks. Yeah.
Nirav, I'd just like to say again a big thanks to all our speakers. It was a really, really interesting afternoon, and I hope to see many of you back next Friday. And of course, thanks to Nira for organizing today's workshop.
Thank you very much. And yeah, we hope to see you all next Friday. Thank you very much. Yeah.